Hello, and welcome to another Wolfram Tech Talk. This is Arben Kalzici. I'm a content developer and instructor with the Wolfram U team. And today we have Dariia Porechna here to tell us about cryptography in the Wolfram language. Dariia?
Hello, Arben.
Hi, how are you?
Hey, good. It's good to be a part of Wolfram Technology Conference again. It's this time of the year.
Mm-hmm.
So,
It came around very fast this year, I feel.
yeah, but well, gotta be online this year again.
Mm-hmm.
And
Yeah.
this year has been different for me as well as a part of Wolfram research because I have tried, being a developer here for like 5 years. This year I have tried another role myself, writing educator content, and it has felt good. And so, yeah, I'm happy to be here.
Yeah, it's really nice to be able to put the knowledge that you have to, I don't know, what feels like really good use when you do educational content versus doing other content. Kind of the rewards are a lot more, I don't know, immediate. It feels nice to just put that stuff out there and see people learning from it.
Well, this has been a lot of work. When you get an immediate reward is like a summer school programs. Like I have done
Yeah.
this, and though you do a lecture and you see people, especially the summer camp kids, like their minds just go bright and
Mm.
you feel rewarded. But writing a full course, the course that I'm writing is Introduction to Cryptography. And it's basically trying to explain not just the cryptography, the way it is used in practice in modern security systems, but all the way to, its history, the basic ciphers, the classic ciphers, and so on and so forth.
Mm.
And this has been a good experience because, as a developer working with cryptography in practice, I'm just using it very, how to say, very low level, like we're talking bits,
Mm-hmm.
and bytes of memory things. And when you try to explain it to other people, you want things to be more visual, more readable.
Yeah, it doesn't do much good to people who are trying to, just learn or even just get an elevator pitch to start talking at the bit level. So it's really nice to, be able to show things in this visual way that you have in this notebook that we're going to be talking about today.
Yes, I was actually going to share now this thing because in Wolfram, you can do cryptography both on a bit level that will give you security, and then you can write about cryptography on example level. And like, I'm amazed. I have been a part of developing this, but I'm still amazed.
Little self-congratulatory, but we'll take it.
Well, I mean, it's been 5 years, so
Yeah,
achieving
five
a
years
lot
of
of
work.
stuff in five
I
years.
guess you get some results after 5 years of work, eh?
Yeah, well, let me share then.
Please
So
do.
I was going to share a snippet from my course. Oops. So this is one of the examples that's talking about stream ciphers.
Hmm.
Stream ciphers are those that encrypt a video frame by frame, basically, as it goes, like in line streams, also in like internet voice calls. And we have an example data that's, this video of a little bird is just bird. You know, I don't know why would someone need
Lovely.
to encrypt this, but let's try.
Maybe there's already hidden information in this bird video that people don't want getting out.
Maybe. So in Wolfram, if you just want to secure your file, you just go encrypt file on it. And you go encrypt file, and it's going to just, save it securely. No one is ever going to look at it. It's going to be bits, ones, and zeros.
Hmm.
The password that I'm using here, password is not exactly secure, but
Not quite, no.
is enough for our purpose right now. And this is what it's going to look like on your computer. This is
Mm.
not very exciting to put
Mm.
in an example. So Wolfram allowed me to get, creative here and make examples that are not present, in other educational things, because you can actually evaluate it. You can go step by step. And I have defined here a key to encryption. I have defined my own encryption function.
Okay, so that key is you go to the image that you're going to encrypt here, and okay, and here you're encrypting just this frame and not the entire video, like in the last example, right?
Yeah, because
Okay,
in encrypt file, it just takes the file and encrypts it. Here,
right.
because the example is about encryption frame by frame, so
Mm-hmm.
that's what I'm trying to do here.
Right.
And I take the image size, basically create the key to be the exact same size. So every
Okay.
byte has its representative in a key and gets encrypted basically separately.
Okay, so the height and width of the image, and then all of the RGB values of each pixel, they get their own random integer from 0 to 255.
Yeah, which
Okay.
is the 8 bits.
Okay.
Yeah, the maximum possible. And then if you encrypt a single frame, it looks encrypted.
Quite encrypted, yes.
It looks quite encrypted. Yes, and like nobody's gonna decrypt it, and this password, is better than password.
Okay, and that logical operator you're using, is there a reason you would use that versus another one, or is this just for kind of the, sake of the example here?
I mean, this is more to keep it simple.
Mm-hmm.
So I'm just storing with random value, and this is a valid cipher. It has been used. It has been used quite a lot during World War II. Basically, you just get your message as long as it is in letters or in bits, and you have the key as long as the message, and you just add each letter or each bit of the key.
I see.
And it has
I
worked.
see.
The
Right.
only issue here is that if you're doing something really big, you need a really big key, and you have to store it
Yeah.
secret.
Yeah, which would make sense in this case. That's maybe why we're not doing the video here. We need quite
We
a
are
few
going to do
keys.
the video.
Oh my God. I guess that
Because
needs.
I've explained it step by step. So first we do a frame, and then we say that we actually do the stream encrypt that is going
Okay.
to do a video frame map on every frame of this video. And it's
Okay.
going to take our initial key and just shift it by a short, just by frame index, again, to keep it simple.
Okay.
Because I could have put the normal encrypt function that you have here in Wolfram, but that were overcomplicated, and that would,
Right.
it would not be obvious that if not for this, it would be still encrypted,
Right. So here you're keeping that kind of same spirit of what you did before, and then as you go forward in the frame list here, you have all those random numbers from 0 to 255, and then all those random numbers get shifted up one, modulo 256, so they go back to 0 if they go over 255. So
Yeah.
you kind of keep the same bit value for that key, but you have a different key for each frame, but it's, you know what the key is for each frame there.
Yes, and that's how also the industrial stream ciphers work. They the key also evolves, so they have some initial key, and then as the video or the stream goes, the key gets generated on the fly based on the initial bytes. And here again, I'm keeping it simple by just adding the frame index, but there are more complicated algorithms to do that. They use
Right.
like shift registers, and I think shift registers are the mostly used. And so doing it frame by frame, you actually do get an encrypted video that is a video that looks encrypted. And I think it's amazing that you can do that with Wolfram.
Oh, yeah. That's I could not tell that was a bird, for example. So for the stream encryption then, what I'm hearing is that when you generate a key for general encryption, the way that key kind of interacts with a given piece of information, in this case a frame here, there are different algorithms for that. So you use that bitwise operation, exclusive OR, but you could use something else. And then in addition to that, if you have multiple pieces of information that you're trying to encrypt, the way that how do I frame this? So you have different ways that the key can interact with the data, but then you can also change the key according to some function. And here it's a pretty simple function, but it could be kind of any arbitrary function that changes the key.
Yeah, I mean, thing about stream ciphers that some of them are still proprietary algorithms, like the ones that are in a decoder of your TV.
Right,
May
right.
not be necessarily known to us, but they usually do have, yes, a specific algorithm that how the key gets generated on the fly. Because if you're encrypting a file, like I did here with encrypt file, it knows beforehand that this video is like 150 megabyte. That's
Right,
it.
right.
If you're streaming, you cannot know that how long will the stream go. You don't know how much time it would take, when it would interrupt.
Okay.
And also, in practice, they take care of possible losses of connection and so on and so forth. So they need to have an algorithm that is both in the sender and in the receiver to derive the key on the fly as long as it needed.
Right. Okay, that makes sense. And you mentioned that, encrypt file in that other notebook there, that one knows ahead of time the size. So kind of like other Wolfram language functions, which are looking at the inputs before deciding specifically what algorithms to use on them. This is doing something similar. So this checks the size of the file and says maybe, okay, well, it's not really feasible to go here and do this sort of algorithm. So I'm going to use a different sort of algorithm that works better for this file.
Well, no, that is not the case. I was just saying that it knows
Oh,
that
okay.
the file size beforehand because it's stored on your system. And so it just reads the whole file and encrypts the whole thing right away. And the algorithm it uses is one of the top-notch and probably one of the most famous symmetric algorithms is IAS. So basically this password inside gets derived into a symmetric key object for the cipher, and it's going to encrypt it with the cipher.
Okay, so 256 bits, that's slightly bigger, you might say, than the 8-bit key we looked at just before.
Well, that key was actually bigger because it was 8 bits per pixel.
Ah, yes, 8
Yes,
bits, yeah, per
so the
pixel,
image,
okay.
if the image is HD, that's large.
Yeah,
But
that's
this is
non-trivial.
actually enough.
Yeah.
Like this cipher has become a standard in 2001, and 256 bits are still like enough for everyday uses of everyone to provide security, because brute forcing, this is all possible amount of keys. And
Yeah,
brute
I guess
forcing that
there's
takes
some time.
more than we have, in a lifetime. Like
Okay.
a fastest supercomputer is still gonna take billions of years to do that for now.
I see.
So, and it's good. It's still small enough that you can store billions of them on any devices we have in the world, and it's still good enough to provide enough security for almost everyone.
Right. Yeah.
So,
Okay.
I mean, I could go on and go on, but this course is like 25 lessons, so I'm not sure you're gonna wish to hear all of that right now.
Yeah, I guess if folks are interested, they can look forward to this cryptography MOOC that will be out. Do you have a time estimate?
I'm not sure, but the lectures are all written and we're currently recording. So
All
just
right.
as soon as it gets through production, we're gonna roll out as soon as it's ready.
Right, and that's going to cover some of the inception, the history, and then it's going to go into more practical applications.
Yeah, so it first 3 lessons are just history from, one of the first famous ciphers is attributed to Caesar. So it goes all the way back there, and then it goes through, some more mathematical ciphers of the Renaissance, and then goes to the First World War and Second World War. There was great push for cryptography. If you watch The Imitation Game, for example, that's also sort of mentioned the Alan Turing cryptanalysis team, and to the modern cryptography and the cipher that I just showed you, EIS, and then tries to explain all of these things, how they actually work and what they do and what are the reasons and what are the maybe underwater stones that can make your security lesser than you think it is. There were historical examples of people that were said you have to use a random number here, but they didn't. And so they weren't actually encrypting anything.
Yeah,
So-
I suppose humans are famously bad random number generators, and depending on what you're using as your generator on your computer, it might not be much better from this perspective.
Sure, but you might even, like there were examples where people, instead of random number, would just put a constant number in their code.
Mhm.
So without even calling a randomizer. So
Yeah, you need a random number, and you're like, a random number, 7. There we go. And you just
yeah,
mash the 7 button in the code. Perfect.
yeah, exactly.
Okay.
Well.
So
Cryptography is about math, and the math of cryptographic algorithm may be secure, but you also have to use it correctly.
Mhm.
And I also try to cover some of that.
Okay.
Right.
So we're covering all of this, and we've got some tips and tricks, for actually using these things correctly.
Yeah. Like,
okay.
Here is the algorithm. Now you know how to implement it, but please don't.
Yeah. Well, we'll see what the success rate on that is. Hopefully, people listen.
Oh well.
All right. Well, thank you so much for your time, Dariia, and it was a pleasure to learn some about cryptography from you, and I look forward to the upcoming Cryptography MOOC.
Well, thank you, Arben, for having me here, and people who are listening, stay tuned for my talk and for the upcoming MOOC.
All right. Thanks so much. Have a good one.
Thank you. You too.
That was Dariia Porechna, a cryptography developer with our blockchain group, and her Wolfram U MOOC will be available sometime in the near future, hopefully soon. And as you've heard, it'll cover everything from the history of cryptography to its uses in the real world, and maybe some tips and tricks to avoid some pitfalls. Stay tuned for more Tech Talks, where we'll be covering everything from differential equations MOOCs to COVID variant analysis to Microsoft Excel integration with Wolfram data types. See you in the next Tech Talk.